Hello friends, welcome to the course Essentials of Data Science with R Software 1, in which we are trying to understand the basic concepts of probability theory and statistical inference. So now you can see, up to now we have understood different types of characteristics of the data, and we have learned that how they can be defined on the basis of theory and how they can be implemented in practice based on a sample of data and using the software. So we will continue on the same lines in this lecture also, and we will try to learn the concept of quantile. And after that I will conclude this lecture by one more topic, Chebyshev inequality. So first let me try to give you an idea of what is the meaning or what is the utility of quantiles and this Chebyshev inequality. Have you heard many times that in certain competitive examination there is a condition that any student who has got the marks more than the say 80th percentile of the board, then the person is eligible to appear in the examination. What is the meaning of this? One thing I would say, don't get confused with the 80 percentage, 80%, 80 percentage, they are different than 80th percentile. Percentage that we know how to calculate means out of 100 what will happen, but this percentile is a different concept. So the first question comes, why do you use such a percentile approach, and how are you going to compute it, and how you can make it more general? Now you know, as a hypothetical situation, we can assume that suppose there are two boards of examinations, say class 10th or class 12th, means anyone you can choose. Suppose we take the class 12th board. So we know at least in our country various states have boards, what we call as a state board, UP board, MP board, West Bengal board, and then we have some central board also like a CBSE, etc. So these are the examination bodies which conduct the examination of the same class level in different places. And suppose suppose there are two boards, board 1 and board 2. Sometimes we hear or people say that okay, this board gives the mark not so easily, and in this board it is very easy to get these marks. What is the meaning of this? Or sometimes people say that okay, the marking in the, say for example, board number 1 is harder than the marking in the board number 2. Means I don't know whether this is true or not, but just for the sake of understanding, for a while you assume that suppose this statement is true, that board 1 has a marking scheme which is harder, and suppose board 2 has a marking scheme which is not so hard, that is lenient. Now what will happen? Suppose there is a question paper in, suppose say mathematics. Now out of 100 marks, a student in the board 1 gets only say 40% of marks, and the student in the board 2 gets 70% marks, means out of 100 they get 40 and 70 marks respectively in board 1 and board 2. Now can you really compare them? You are saying that okay, the board number 1 has a hard marking scheme that it does not give the mark so easily, and it will take out the mark even for a single mistake, but in the board 2 the marking scheme is lenient. They will not bother about, for example, say this smaller mistakes. So now can you compare the two students having the 40% marks and 70% marks? Certainly not, because it is possible that the student in the board 1 is far much better than the student in the board 2 as far as the concepts are concerned. So, the question is this: you cannot compare by percentage. So, what to do? One simple option is this: when the students are appearing board 1 and in board 2, then the marking scheme within board 1 is homogeneous and within board 2 that is also homogeneous. They are similar. They are not comparable when they are trying to compare according to the boards. So, now inside the board 1, if there are 2 students, somebody has got 40% and somebody has got 60%, I can say very easily that the student with the 60% mark is better than the student with 40% marks, and same thing is true for the board 2 also. But when we are trying to compare the 2 boards, then they are not comparable. So, what we try to do? We try to take the marks of the board 1 and we try to divide the minimum and maximum marks as 0 or and 100. And then we try to create the probability distribution and we try to create 100 parts of the distribution of marks. And the same thing I try to do in the board 2 also, that minimum and maximum marks, they are equated as say 0 and 100, and then we try to make 100 partition of the distribution of the marks in the board 2. Now, what will happen? That in the suppose in the 80th partition of the marks in board 1, suppose that comes out to be only say here 50, and the 80th partition in the board 2 comes out to be suppose here 90. So, that means within that group, whatever are the students at the 80th positions in their respective board, they are comparable. That is a way how we can think of comparison. So, this concept is called actually quantile, and in particular this case when we are trying to create 100 partition, these partitions are called as percentile, right. So, this is how this quantile concept helps us in data sciences whenever we are trying to compare the values in the 2 data sets, right. People also try to compute different types of probabilities using the quantile of a distribution. For example, if somebody wants to know what is the probability that the total number of people in who are visiting a shopping website are in the top 5%, right, what is the probability? So, then that means they have to simply compute the 95th percentile, and then they have to see that how many people are lying in the interval from 95th onwards to 100th percentile. So, this is a very useful concept, right. So, that is what we are going to learn here, number 1. The second concept which I am going to deal in this lecture is about the Chebyshev inequality. Whenever you are trying to find out the probability of an event, you always try to approximate it using some probability function. It can be for a discrete random variable or a continuous random variable. But definitely you are trying to compute the probability on the basis of some given set of observations, right, and this probability may not be 100% accurate. In that case, you would like to see, okay, what is the minimum value of the probability beyond which we cannot go, or means if you try to find out the probability of certain event and if you try to find out that, okay, the probability cannot be lower than this, then these types of statements, they really help us in data sciences when we are trying to work with the real data, because ultimately your objective is that you want to get the correct statistical inference. So, Chebyshev inequality helps in finding out the such probabilities. So, if you can find out the probabilities using the Chebyshev inequality, suppose this comes out to be 0.3, right. and your estimated probability is suppose 0.5. So, you can see that okay, I am trying to compute it as 0.5, and if I try to take another sample, possibly that may come to say 4 also, but in any case that cannot go beyond 0.3. So, these types of statements are drawn using the Chebyshev inequality, which is a very simple thing, but it is, I personally believe that it is important for you to understand. So, let us try to begin our lecture and try to first understand the quantile concept. So, we define the quantiles in terms of distribution function, and you know this was your cumulative distribution function which you had indicated as CDF. So, suppose there is a value xp. So, this value xp for which the CDF is given by f of xp is equal to p, where p is some value lying between 0 and 1 is called the pth quantile or p quantile, right. So, what is this value xp doing here? Xp is the value which divides the CDF into two parts. The first part is the probability of observing a value left of xp is p, whereas the second part is the probability of observing a value right of xp is 1 minus p, right. So, for example, if you say we have the 0.25 quantile which will be indicated by x subscript 0.25, this will describe the x value for which the probability of observing this value x 0.25 or any smaller value is 0.25, right. So, that is as simple as that. So, for example, if you try to see here, suppose this is the CDF of some random variable here x, and if you try to see here, this x 0.25 is the value which is trying to divide it such that this area, which I can highlight here, this is actually 25% of the total area, or it is 0.25. Right. And similarly, if you try to divide this total part into two equal parts, so this will be x 0.50. So, this will be then area which is trying to cover this area, right. So, this will be your here the value of x which is trying to divide the CDF into two parts such that the area below this value and above this value they are the same, say 0.5, 0.5 each. And similarly, if you try to take here say x 0.75, then that means x 0.75 is the value which is trying to divide the CDF into two parts such that the area below this value which is up to here, this is 0.75, and the area beyond this thing, this is just 0.25, right. So, this I can call it x 0.25 is my 0.25 quantile, and x 0.5 is my 0.5 quantile, and x 0.75 is my 0.75 quantile, or they are called as say here first quantile, second quantile, or the third quantile, right, of the CDF. And actually this second quantile is called the median, that you know, that you have learnt in your undergraduate classes, or even the high school or class 12th also, that what is called the median. Median is the value which divides the total frequency into two equal parts, and you can see here this median is the value which is trying to divide the total area of CDF into two equal parts, right. So, the second quartile is nothing but your median. So, first quartile, second quartile, and third quartile. You have to be careful. I am using here two sounds and two words. One here is quantile and another here is quartile, right. So, this what I have written here, this is first quartile, and this is here second quartile which is median, and third quartile which is here 0.75 quantile. Okay, just be careful with my sound and y. So, this is what I have tried to define here, the same quantiles. They can also be called as 25% quantile, 50% quantile, and so 25% quantile, that splits the data into two parts, such that at least 25% of the values are less than or equal to the quantile value, and at least 75% of the values are greater than or equal to the quantile value. And similarly, the 50% quantile is split the data into two parts, such that at least 50% of the values of are less than or equal to the quantile, and at least 50% of the values are greater than or equal to the quantile. And this 50% quantile is actually called as median, right. So, now in general I can define here that alpha into 100% quantile is the value which divides the data in proportions of alpha into 100% and 1 minus alpha into 100%, such that at least alpha into 100% of the values are less than or equal to the quantile, and at least 1 minus alpha into 100% of the values are greater than or equal to the quantile. And if you are getting confused with this language, I will say simply try to put here alpha is equal to 0.25, 0.5, 0.75, and try to understand the interpretation what I have given here in this curve, in this graph, right. So, whenever we are trying to divide the given data or the total frequency into 4 equal parts, they are called as quartile, and they are indicated by Q1, Q2, Q3, Q4. That is standard symbols in the applied statistics. So, Q1 is the first quartile, which has 25% of the observation. Q2 is the second quartile, which has 50% of the observation, which is called as median, and Q3 is the third quartile, which has 75% of the observations, and Q4 is the fourth quartile, which has 100% of the observation. And you have seen that these types of terminology are very well used in real data application. People always want to know that how the data is partitioned into different values. For example, you can see that whenever we have some sort of special shopping days which are advertised heavily by some shopping websites, what you can see here, that if there are suppose say 1 million customers which are going to access the website, suppose in the 3 days of time, then you see that as soon as the sale begins, the number of customers which are trying to access the website in the beginning, they are much higher than those who are in the middle part. So, now in this case, do you think that the number of customers in the first couple of hours, they are going to be the same as in the last couple of hours? No, that is not going to be a symmetric distribution, and under this situation the concept of quantiles helps us in making different types of comparison. Okay. So, similarly, if you try to divide the total frequency into 10 equal parts, then this is called as deciles, and they are indicated by D1, D2, D10. So, D1 is the first decile that has 10% of the observation. Similarly, D2 has 20% of the observation. Similarly, D5 has 50% of the observation, and this is called as fifth decile, and D9 is the ninth decile, which has 90% of the observations, right. And similarly, if you want to divide the total frequency or the of the given data into 100 equal parts, P1, P2, say P100, then this is called as percentile. That is the same thing about which I took the example in the beginning. So, P1 is going to be the first percentile, which has just 1% of the total observations. P2 is the second percentile, which has just 2% of the total observation. Similarly, P50, now you can understand this is the 50th percentile, which has 50% of the observation, and that is called as median, right. So, similarly, the 90th percentile is indicated by P90, and it has 90% of the observation. So, these concepts helps you a lot, but the main thing here is this, how to compute them in the R software, right. So, computation of these quantities in the R software is very easy. For that, we have a command here quantile, QUANTILE, and inside the parenthesis you have to give the data vector x, and there are several options that you can give, but I will try to take here only one option here, PROBS props, to illustrate that how you can compute different types of percentile. And in this case, for example, x is going to be the numeric vector or the data vector for which we want to compute the quantiles, and props is PROBS, that is going to indicate the probabilities, means you want to partition the total area under different types of partitions, and these partitions may be of equal size or they may be of unequal size, like as you can see here, if the distribution is like this, I want this point and this point. So, since the area under the curve, that is actually the probability density function or probability curve. So, this area is always going to be 1, and this one area is going to be divided it into say the required number of partition according to our choice. So, this props function is going to help us in fixing those sizes, right. So, this props is a numeric vector of probabilities whose values will always be between 0 and 1, and type is an integer between 1 and 9, selecting one of the 9 quantile algorithms. Why? Because you see, whenever you are trying to compute such partition, they are not computed by a simple methodology, but some algorithm is used to compute these partitions, and different people have given different types of these algorithms. So, these algorithms are going to certainly give you different values, but definitely these values are not going to differ much. So, in practice, even unless and until you have a specific requirement, you can use any of the algorithm. For example, in case if you give here type 1, the type 1 is based on the inverse of empirical distribution function, type 2 is based on say type 1, but it is a little bit different, that it is related to the averaging at discontinuities. Type 3 is the say based on nearest even order statistics and so on. So, I am not going into that detail, but my objective here is to show you how to compute these partitions, right. So, suppose let me try to take an example here to illustrate that how these things are working, because they are more useful in application. So, their application is more important for you to learn. Suppose I take here only 50 observations, and these are the observations on the heights of 50 persons, and they are recorded in centimeter. Well, I am taking here only 50 observation, because if I try to take more observation, it is not possible for me to show you clearly on this screen, on this slide, right. But yes, this small example will give you more ideas. So, I try to store these values in a data vector here height, and then I try to find out here the quantile height on the R console. Right. Now, if you try to see how are you going to interpret it, as soon as you give this function over here, you will get an outcome like this one, right. So, this will start from 0th quantile, and then it will come to 25th quantile, right. Quantile, and this will be the 50th quantile, and this is the 75th quantile, and this is here the 100th quantile. So, this is going to be the 100th quantile, which is going to be the maximum value, because I will try to show you on the R console, and this 0%, that is going to be give you the minimum value also, that is the same as minimum value, and this 137.5, this is the 25th percentile, 146.5 is the 50th percentile, this 158.0 is the 75th percentile. So, they are trying to give us the value of Q1, Q2, Q3, Q4. So, this is the value of Q1, this is the value of Q2, this is the value of here Q3, and this is the value of here Q4. I will try to show you on the R console also, but first we try to have a look, and then I will try to show you means other things. So, let me try to copy here this data, that will save my time. So, this is my here data, and you can see here this data is like this. Okay. So, now we try to operate the quantile function on this data vector height. So, you can see here these are here the height. So, this is going to be the 25th quantile, which is the first quartile having the value 137.5. This is the 50th quantile, or this is the second quartile whose value is 146.5. This is here the 75th quantile or the third quartile whose value is 158, and this is here the 100th percentile, or this is the fourth quartile whose value is 166. So, as I told you that this 0 and 100% quantiles are the minimum and maximum value. So, let us try to verify this thing. So, if you try to see here the minimum value of this data vector height is here 121, which is same as here like this one, and the maximum value of this data vector is 166, which is here this value. So, you can see here that this quantile function has divided the range of 121 to 166 into 100 equal parts, right. So, but now definitely you would have one more option, that you do not need these partitions to be of the equal size. So, now how to get it done? So, for that we are going to use the option here, say props. So, props, for example, if I try to take here sequence 0 to 1 at an interval of 0.25. So, you know sequence 0 to 1 means this is starting from 0 to 1, and this is here by. So, 0.25. So, definitely this sequence is going to generate a set of values like this one, 0, 0.25, 0.5, 0.75 and 1. So, now if you try to put here the quantile of the same data set heights, but if you try to take here props equal to sequence 0 to 1 0.25. So, you can see here what are you trying to do? You are trying to divide the entire data values into 25%, 50%, 75%. That means you are simply trying to find out the quartiles. So, you can see here that in case if you try to operate it on the R console, you will get here the same value, right. And if you try to compare it with here these values, where you have given only the variable name height without the props function, you are getting here the same value, right. So, this is what I wanted to show you, so that you are confident that when we are trying to use the props function is simply trying to divide the entire data into different partitions. When you want to have equal size partition, you can give it, or you want to have only 4 partitions, you can give the values to be here 0, 0.25, 0.5, 0.75 and 1, and in case if you want to change it, you can always change it, right. So, for example, this is the screenshot of the same operation. I will try to show you on the R console also, but before that means if I try to change my props function, and if I try to take it here sequence from 0 to 1 by 0.1, that means you are going to get here 10 values starting from 0.0 to 1 and at an interval of 0.1. So, the values will be 0.0, 0.1, 0.2 up to 0.9 and then finally 1. So, now if you try to use this props function in the quantile function, then you are giving here props equal to sequence 0 to 1 by 0.1, and now you can see here the outcome. The outcome will look like here this. So, what are these things? They are trying to divide the total values into 10 partitions, and this is called as deciles, and they are the values of D1, D2, D10. For example, this is here the value of here is this 0% percentile, this is the value of here 10% say here quantile. I can say that at 0 whatever you want you can call it, because it is the 0th quartile or 0th percentile or 0th quantile, but for 10% this is the value of here D1, which is here 126.8. This is the value of here say here D2, which is 134.6. This is the value of here D3, which is the value of here third decile, and this is the value of here 4, third decile 143, and similarly here you can see here, or you have obtained all the deciles, or you have partitioned the total frequency into same size, but having 10 partitions. So, you can see here this is the screenshot. And similarly, if you try to use here the option props equal to sequence 0 to 1 at an interval of 0.01, this will create 100 values, and in case if you try to use this props function inside the quantile function, what do you expect? That will give you the values of percentile. So, you can see here now, in case if I try to use here the quantile function with the props equal to sequence from 0 to 1 by 0.01, then it is going to give you here this type of outcome, where you can see, for example, if I try to say here, suppose this value, what is this thing? This is the 58 quantile, or this is 58 percentile. And similarly, if you try to look at here, this is 92% quantile, and this is the 92th percentile. So, now you can see here, once you say that during an exam, anybody who is going to get, suppose more than the marks of 80th percentile, that student is going to be eligible to appear in the exam. That means, I simply have to find out here this value. So, 80th percentile is just 159.00 marks. So, means any student who has got the marks more than 159, that person is eligible to appear in the exam, right. And you can see here, this is the screenshot of the same operation what I have just shown you. And now, let me try to show you these outcomes what we have obtained here for deciles and percentiles, etc., whether they really hold or not. So, now I try to find out here the same function here, say here quantile, you can, but by using the props command, you can see here that this was your here quantile height, that is giving you 4 quartiles, and now you are taking here the props function. So, this is again giving you the quartiles, right. Now, similarly, if you want to find out here, say here, you want to divide it into 10 equal parts. So, you have to simply make here the quantile of height props equal to starting from 0 to 1 at an interval of 0.1, and this will give you here 10 values, which are D1, D2, D10. And similarly, in case if you try to make here 100 partition, that means you have to control only the props function by writing sequence 0, 1, 0.01, and it will give you here such 100 values. You can see here, this is here the 100 values, 100th value actually, right. So, this is our percentile. And similarly, if you want to make it here at an interval of say here 0.33, right. So, even that is possible. You can see here, this is giving you any type of value. So, remember one thing, we are going to use this function when we are trying to use the part, when we are going to learn the part of statistical inference. At that moment, I will remind you that we already have computed, or we already have learned how to compute these different types of quantiles or percentiles. Now, I come to the last topic of this lecture, which is about the Chebyshev inequality. So, one thing you have to be very careful that how to say this word. So, this is Chebyshev, right. So, now this Chebyshev inequality helps us in those situations when we do not know the distribution of the random variable x, but we still want to make some statement about the probability, right. So, even when we do not have any idea about the probability distribution of x, well, at this moment you may not understand, but just after this I am going to start with different types of probability distribution functions and probability mass functions. So, you will see that the random variable will always have some probability function, and now suppose you do not know, but if you want to make certain statement about the probability, then we can use the concept of Chebyshev inequality, and in this case the x takes values in a certain interval, right, and the condition is this value has to be symmetric around the expectation, that is mean mu, right. So, in case if x is taking the values in certain interval, if the mean is mu and the variance of x is sigma square, and both mu and sigma square are known to us. In that case, the statement of Chebyshev inequality is that if expected value of x is mu and variance of x is sigma square, remember one thing, what will be the PDF or PMF of x, that we do not know. In this case, the statement is simply trying to say here probability that absolute value of x minus mu is greater than or equal to c, that is going to be smaller than or less than equal to this quantity variance of x divided by c square, right. And the same thing can also be written in this format, that the probability that the absolute value of x minus mu is less than c, this is going to be greater than or equal to 1 minus variance of x upon c square. Now, if you try to see, sometimes students get badly confused with this symbol and notation, but this is very simple. What are you trying to say? If you are trying to say here x minus mu is suppose less than c, right, what does this mean? So, this means x minus mu is going to lie between minus c and plus c, that means x is going to lie between mu minus c and mu plus c, right. So, if you try to see here, when you are trying to take here this quantity x minus mu, this is only the deviation from mean, and this quantity is very important, that whenever you get your marks in a test, you always try to measure it from your mean. Whenever you go to your home and your parents ask you that how is your performance in the exam, you always try to compare your marks with the class average. In case if the difference between your marks and class average is quite large, then possibly you are on the extreme. For example, if the class average is suppose 60 marks and you have got only say 20 marks, then the performance in the examination is bad, and if you have got say 90% mark, that means the performance is very good in the examination. But in case if the class average is suppose 90% and somebody has got the marks say just 91% or say 70%, this will have a different interpretation. So, we want to compute this type of probability, right. So, let me try to take a small example to show you that what will be the difference between computation of a probability directly from the probability function and using this Chebyshev inequality. So, let me try to take the same example that I have considered earlier many times, that there is a continuous random variable indicating the waiting time of the train, and suppose the train arrives after every 20 minutes. So, the waiting time for a particular person will be random between 0 and 20 minutes, and the required probability density function in this case, this is here f x equal to 1 upon 20. Now, suppose we do not know this f x, but suppose you know the value of here mean and variance, and for that means we can just compute it. So, mean is going to be that we already have computed that expected value of x, which is coming out to be here 10, and sigma square is the variance of x, which is coming out to be 100 upon 3, that we already had computed in the earlier lecture. So, now suppose you do not know the PDF, but you simply know the value of mean and variance, that is mu and sigma square. So, now we can calculate the probability of waiting time between 10 minus 7 3 and 10 plus 7 is equal to 17 minutes, right. So, now using the Chebyshev inequality, I can write down here probability that absolute value of x minus mu is smaller than c, that can be written as probability that absolute value of x minus 10 mu is here 10 is less than 7. 7 is the deviation from the say x minus mu. You can see here in this question, this is what we are writing here. Right. Now, this is going to be is greater than or equal to 1 minus variance of x that we have computed to be 100 divided by 3, and this is c square. C square is here 7 square, because c here is 7, and if you try to approximate it, this will come out to be 0.32. Right. So, probability is therefore at least 32%. That is what you have to understand. That is the interpretation, that the probability is therefore at least. Now, in case if we try to say use this probability function, and we try to obtain the distribution function, that will come out to be like this: capital F x equal to x upon 20 for x lying between 0 to 20. And if we try to obtain the more precise result for this event, then I can simply write down here that x is lying between 3 and 17, which is equal to f 17 minus f 3, that we already have learned that if you want to find out such probabilities using the CDF, how you can find it out. So, this will come out to be here 17 upon 20 minus 3 upon 20. That is the same example that I had conducted that I had considered earlier also. So, this probability comes out to be here 0.7. So, now you can see here, this is the exact probability, and this is here the probability in terms of at least. Right. So, what you can see here the connection. From the Chebyshev inequality, you are getting the probability at least, which is 0.32 approximately, and using the PDF, you are getting this probability to be 0.7. So, we can very clearly see here that the Chebyshev inequality gives us the correct answer, that is probability that x is lying between 3 and 70 is greater than 0.32. The exact probability here is 0.7, is rather poor for approximate probability. Well, it depends that what type of C are you going to choose. So, my idea is that I am not trying to criticize the Chebyshev inequality or any probability, but I want to explain you here both the concept, and depending on the situation you have to choose what you want to do, whether you want to employ the Chebyshev inequality or you want to compute the exact probability. That depends on your objective. That I cannot tell you at this moment. My objective is to make you learn all the possible things. Right. So, one needs to keep in mind that only the lack of distributional knowledge makes the inequality useful. But because once you do not know that what is your probability function, what are you going to do? You have to choose something. So, in that way this is going to help you. Okay, so, now we come to an end to this lecture, and you can see here we have considered the topics of movements, quantiles in this chapter, in this section, and the movements are going to give us a very realistic information about what is happening inside the data set, and then quantiles are also giving us the values of say partitioning the data set. So, these are the different partitions. Now, it depends on you. In data science, whenever you are trying to deal with huge data set, you cannot view those data set by your eyes. There can be millions, billions and trillions of observations, say not only gigabyte or but the terabyte. The data may be in terms of petabytes. So, you cannot view that data with your eyes, but you have to depend on these tools to take out the hidden information from the data. This hidden information will be the statistical information, and the statistical information will be in terms of movements like as mean, variance, skewness, kurtosis, etc. Now, the question is, where are you going to use mean and where you are going to use the skewness? That is up to you. But my opinion and my suggestion is that when the data comes to you, the data cannot speak. Data cannot raise the hand and can say, okay, I have this property. So, we try to implement all sorts of tools, graphical, analytical. We will try to find out the mean, variance, skewness, kurtosis, and finally, we try to gather different type of information so that we can take a correct conclusion. So, now I will say try to take some example from the assignment, from the books, and try to understand these topics, they are surely going to help you when you are really going to work in data science. So, you try to practice, and I will see you in the next lecture with a new topic on probability functions. Till then, goodbye.